Okay, in this problem we're asked a question about a fixed charge, charge number 1, and a moving charge, charge number 2. Now initially, charge number 2 starts 0.6 millimeters away from charge 1 and is moving towards it, but we're asked to find what the speed of that charge is when it's far, far away. In order to get an idea of what's happening here, let's take a look and see how the motion of the charges go. So number 1 is fixed. Number 2 is initially moving towards number 1, but it's going to be decelerated. That is, it will have a force opposing its motion because these charges are both positive. So charge number 2 is going to eventually slow down and stop as it approaches charge number 1. At the point of stop, though, it won't stay there because there's still force that's being exerted on a repulsion, and so it's going to be accelerated the other way. And in fact, it's continued to be accelerated until it's far from charge number 1, and the Coulomb acceleration drops to 0 with the 1 over r squared power of Coulomb's law. And so our task here is to figure out how fast the charge is moving when it's very far away from the initial charge. It's fixed. So how are we going to do this? Well, the easy thing to do is use the work energy theorem and the fact that the kinetic energy is conserved. If we use that fact, then we don't have to concern ourselves with the details of the motion. We just have to examine the initial kinetic and potential energy, and then examine the final kinetic and potential energy in order to figure out how fast the charge is moving. Okay, so let's look at these quantities. The easiest quantity here is the final potential energy. The problem asks for the motion when the charge is very far away. Well, since the potential energy drops off as 1 over r, eventually if the charge gets far enough away, it's going to have a 0 potential energy. So that term's pretty easy. There's no potential energy once the charges are extremely far apart from one another, at least approximately 0. Okay, what about the other energies? Well, the kinetic energy initial is essentially given in the problem. We're told the charge is moving at 25 meters per second, and we're given its mass. So we can solve for this value just using the fact that the kinetic energy is 1/2 the initial velocity squared times the mass. If I put in the numbers, now note that we're given that the mass of the particle is 105 milligrams. That means it's 105 microkilograms, so 105 times 10 to the minus 6 kilograms. Again, we want to work in SI units in order to be consistent. That's initially moving 25 meters per second. And so I can calculate the initial kinetic energy. It turns out by multiplying this together, this is 32.8 millijoules. So we know the initial kinetic energy, and we know the final potential energy. Let's fill in the rest of the pieces. What's the initial potential energy? Well, in general, for two charges, potential energy between the two of them is Q1 and Q2 over 4 pi epsilon naught times 1 over r. So it represents the potential energy. And we can calculate this because we actually know all these values for the initial condition. For instance, charge 1 is equal to 100 nanocoulombs. Charge 2 is equal to 45 nanocoulombs. Then we have a constant, 1 over 4 pi, 8.85 times 5 times 10 to the minus 12 coulomb squared per joules meters times the initial separation, which is 0.6 millimeters. That's 6 times 10 to the minus 4 meters. Again, I want to work in consistent SI units. Okay, I can put all these numbers together and multiply them out and find that the initial potential energy is 0.0674 joules or 67.4 millijoules. Okay, so I've calculated the initial energy for both potential and kinetic, and I know that the final potential energy is 0. But I don't know the kinetic energy in the final condition. I do know that's equal 1/2 times the speed of the particle squared once the particles have moved infinitely far apart. And then using the work energy theorem, since the final potential energy is 0, I know this 1/2 mv final squared is just going to be equal to the initial kinetic energy plus the initial potential energy. I calculate those two things. So this is 0.0328 joules plus 0.0674 joules. I can total those two things up. And I can find that the total energy is actually 100.2 millijoules, or 0.1002 joules. Okay, by equating this to the final kinetic energy, I can solve for the velocity. This means 1/2 times the mass times the final velocity squared is equal to 0.1002 joules. By doing more algebra, I can solve for the final velocity. I find that the final velocity is equal to 43.7 meters per second.